Hi all, this is Mr. Yeager for chemistry. We are now moving into the applications of stoichiometry, which is limiting reactant and percent yield. This may be 2 videos, we'll see how this kind of goes, because both these problems do take some time to basically finish up. We don't really add anything, we only add a couple little things to the actual application of it, but it's mainly mass-to-mass stoichiometry, which is what we're about to do, okay, is the primary technique and tool that we're going to use to figure these things out. So here we go. And another teacher in my group, chemistry group, made this, and again, I appreciate all that they do. The limiting reactants. All right. So as the name implies, okay, when we do a reaction, we are, and we have multiple reactants. There's one reactant that's going to run out before all the other ones. I mean, if you think about that, even with the back end the analogy with cooking. All right, there's always something that limits your ability to do more. You can even talk about if you built something and you have a certain number of screws and you lose one, there's going to be a certain spot where it might stop you from finishing building what you're doing, okay, unless you get a new one. So the limiting reactant is the thing that runs out first, and when that runs out, that's where you finish, and that's how much product we're going to have in the chemical reaction itself, okay? So it will tell, the limiting reactant tells you how much you will produce because it's the first thing that goes away. So that's the limiting reactant. There is the excess reactant. Obviously, this is the other one. So this would be the one where the reaction could keep going, but because the limiting reactant runs out, we do use, obviously, a lot of the second reactant, but whatever's still left obviously is excess, which is why we call it excess reactant. So we will be calculating how much reactant of the other one is left over. So we have a limiting reactant and an excess reactant. The limiting will go to 0. The excess reactant, we will figure out how much is left of that. Okay? So how do we solve these? Obviously read the problem, balance the equation, all right? And then you start with the given amount of each reactant. So you're going to be doing basically 2 mass-to-mass stoichiometries. Go to the product that is asked for in the problem. All right? And you're going to do 2 mass-to-mass with each reactant to that product, each reactant to the same product. And whichever one produces less is your limiting reactant. And if you do it this way, you usually solve 2 problems at the same time. You figure out what the limiting reactant is, and you figure out how much product is formed at the exact same time. Okay? You also figure out what the excess reactant is, but then you still have to do one more thing to figure out how much is left. Okay? So here we go. So limiting reactant. If 1 mole of HF are exposed, what is the limiting reactant? Okay. All right, this was not the way I was expecting this to start, sorry. So anyway, but we'll do it. We can do it with mole, okay? This one's just saying what is the limiting reactant. So because it doesn't tell us what to go to, we can just go ahead and pick any of the products. And you don't have to go all the way to mass. You can just go to moles of the product, and whichever one produces less moles is fine to do. So we do have to balance it. So 1 SI, 1 SI, 2 O's, 1 O. Need to put a 2 there. I have 1 F, H, 1 H, 4 H's, so 4 and 4 and 4. So what we would do here is we would do 2 mole-to-mole calculations. So sorry, you don't always have to go to mass-to-mass. That's what I'm generally used to. Again, sometimes that's generally what we've done in the past, but this time we might be just going mole-to-mole, which is fine. So 1.0 moles of HF, and I'm going to just pick SIF to go to. So if I'm in moles, I can go to moles. I'm coming from moles, I should say, and I can go to moles of any other product reactant in this, and that's going to be SI4 in this case, F4. And the ratio is 4 to 1, and if I have 1 mole of HF, it can produce 0.25 moles of SIF4. Now I need to see what the SiO2 does. I have 4.5 moles of SiO2. I come from moles of SiO2, go 2 moles of SiF4. This is a 1-to-1 ratio, again coming from our coefficients, and I can make 4.5 moles of SiF4 if all of the SiO2 runs out. So which reactant is producing less? The HF. So HF is my limiting reactant. That's my answer. SiO2 would be my excess reactant. Okay? I guess we're playing with moles. That's all good. That makes us, this actually should make it a lot easier then. All right. So I got to balance it. So I got 4 and 3. This is a nice, easy synthesis reaction to do. I have 4 moles of phosphorus is what I'm starting with. 4.0, sorry, I should keep sig figs. And obviously there's only one product, so I'm going from moles of P to moles of P4S3. And there's a 1 in front of P4S3 and a 4 in front of P. And these 4 moles of P will make just 1 mole of P4S3. All right, so that was P. If you want, you can like write P in front of it so you know which reactant you're playing with. This would be S. S, I have 1.5 moles of S. And I'm going from moles of S to moles of the product, P4S3. 3 to 1. This comes out to 0.5 moles of P4S3. Okay? So which one's my limiting reactant? It's the one that produces less. That will be S in this case. Now, I'm going to warn you. You're probably sitting there going, why are we even calculating? It had less moles at the beginning. And so did the other problem. The other problem, the one that had less moles, was the one that created less moles. That's not always going to be the case. We're pretty close here, okay? 4 is a lot larger than 1.5, but in the end, it only produced double what the other one did, okay? So don't think, oh, I found a trick now, and if I just look at the very beginning, that's going to be my answer. You're not going to be right, okay, all the time. You might get lucky, but you won't be able to prove it. That's the other thing, is you still need to prove it, okay, is what's going on with this. All right, 500 moles and 750 moles. Maybe we're only doing mole to mole. Okay, that's pretty cool. All right, so I have 2 H's, I have 4 H's, so there's 2 right there, and 1 CO, 1 C, 1 C, 1 O, 1 O, we're good. All right, so I have 500 moles of CO. Sorry, CO is my first reactant. H2 is my other reactant. 500 moles. So I'm going from moles of CO to moles of CH3OH. This is 1 to 1. And this comes out to 500 moles. That's a lot of moles. Okay. Of CH3COO. Oh, what am I doing? CH3OH. All right. Second, I have 750 moles of H2 coming from moles of H2 to moles of CH3OH. I have 2 moles of that and 1 based on the coefficients. Oh, it finally happens. This is going to be 300, technically 80 with the sig figs. Yes, 375, but 380 moles of CH3OH. So it finally happened. This is what I said I warned you about. The limiting reactant is going to be H2, even though there's more moles present based on the chemical equation and how I need 2 H2s for every CO. It would only produce 380 CH3COH molecules at the end. So H2 is my limiting reactant, CO is my excess reactant. Here we go. Okay, this is what I was kind of expecting. What if we are given grams? Well, technically, again, we could figure out the number of moles and figure out how much is produced, okay? How much product is made, all right? I am going to now do this as, when I start seeing this, I know I wasn't doing it before, how much product is made, I want to go to grams when that is the case. Okay, I should have probably been doing that on the other problems, but I was just trying to identify the limiting reactant, so we'll do it now with this one. So 4, 4, 2, 10, this is going to be a 5. All right, so I need to figure out which one's the limiting reactant, and I want to know how much will be produced of P4O10. So I start with P4, I have 25.0 grams, I'll write P4 over here, of P4, I'll even write it in there. I'm going to go from grams of P4 to moles of P4. So this is the molar mass. We do 30.97 times 4. I get 123.88 grams. All right, I'm now in moles, so I can now go from moles of P4 to moles of P4O10. Based on the reaction, this is just 1 to 1. And then I go 1 mole of P4O10 to grams of P4O10. And so that would be 283.88 grams. That's the molar mass. And so if I do all this, 25 times 283.88 divided by 123.88, I should produce 57.3 grams if all of the phosphorus reacts. What about the 50 grams of oxygen? 50.0 grams of O2. Grams to moles. There's 32 grams per 1 mole of oxygen molecule. I'm going to go from moles of O2 to moles of P4O10. 1 to 5. And then moles of P4O10 to moles of, not moles, sorry, grams of P4O10. Now you don't have to recalculate this, you have it above, so this is still 283.88. All right, let's see how much this would produce. 50 times 283.88 divided by 32 divided by 5. This is going to produce 88.7 grams. So the answer to my question is, how much product is produced? It'll be 57.3 grams of P4O10, because P4 is my limiting reactant because it's producing less product. I think we might have one more here. We're going to just do one more. Last one for us. So if you want to pause this and look at it and try to solve it on your own, go ahead. If not, here we go. So we balance this out. I have 2 H's, 12 H's, that's 6. I'm going to skip the O's for now. I have 1 and 6, so 6. I now have 6 plus 12 is 18. I have 6 from here. I need 12, so this is going to be 6 as well. Good. All right. So CO2. I have 88.0 grams of CO2 coming from grams of CO2. All right. Sorry. We should stop for a second. I should finish reading the problem. It says determine the mass of glucose. Glucose is this guy right here. Okay. So I'm going to go from mass of CO2 to mass of glucose. So grams of CO2, moles of CO2, 1 mole, and this is 44.01 grams. That cancels out. I'm now in moles of CO2, going to moles of C6H12O6. This is 1 from the reaction, 6 from the chemical reaction. I now know how many moles I'm making. Moles of C6H12O6. Grams of this, 1 mole. All right, I am rounding this one just to go a little faster. This is basically 180. And we can solve. So 88 times 180 divided by 44.01 divided by 6. So if all 88 grams of CO2 reacts, I will create 59. Technically it rounds up to 60.0 grams of glucose. What about the water? I have 64.0 grams of water. Okay, I go from grams of water to moles. This is 18.02 grams, 1 mole. Then I have moles of water going to moles of glucose. This one also is 1 to 6. And then I have moles of glucose to grams, 180 for 1 mole. Let's see what I get here, 64 times 180 divided by 18.02 divided by 6. if all this water reacts, I'll get 107 grams of glucose. So which one is less? This. So I'm going to create 60 grams of glucose. This is my limiting reactant. Okay. That is what we are looking for here, and we are not going to have to find the excess reactant. You just have to be able to identify it or define what the excess reactant, but that would be it. All right. So take some time to practice, and you are good to go. Thank you.